Hey everyone, this is Dr. Habib Ahmed. Welcome back to the channel. Today we will explore how to set up compositional grading profiles in ternary alloys using Silvaco TCAD. So what is compositional grading? It is when the material composition in an alloy, for example indium gallium arsenide or aluminum gallium nitride, changes smoothly across a layer. This grading can adjust properties like the bandgap or lattice constant to improve device performance. For example, in solar cells or LEDs, it helps reduce defects, improve efficiency, and manage strain. It is simple, practical, and perfect for advanced device designs. If you are excited to learn more, like, comment, and subscribe for more Silvaco TCAD tutorials. Compositional grading has many applications. For example, solar cell for smoother bandgap transitions and higher efficiency. LEDs and lasers to improve light emission and reduce defects. High electron mobility transistors for better strain management and performance. Photodetectors to enhance sensitivity across a wider wavelength range. So you can use this technique in Silvaco TCAD to optimize your device designs. Now, I'm not specifically going to implement any particular kind of device in today's lecture, but the focus is going to demonstrate how to perform compositional grading. And then you can use it accordingly for your own applications. So, the structure that on which I'm going to implement the compositional grading starts with a sapphire layer. Then we have a thin aluminum nitride nucleation layer. Then we have a thick gallium nitride buffer layer. And then we have this 200 nanometers aluminum gallium nitride film. And I'm going to demonstrate the compositional grading on this 200 nanometers aluminum gallium nitride film. And basically, I slightly adjusted this structure from one of my previous high electron mobility transistor simulations using Silvaco TCAD. In the actual HEMT structure, this aluminum gallium nitride layer was 20 nanometers or 30 nanometers. But here, I have increased the thickness of the aluminum gallium nitride film so that I can better demonstrate the concept of compositional grading over a thickness of 200 nanometers for aluminum gallium nitride film. And then you can adjust it accordingly for your own kind of materials. You may apply it to indium gallium arsenide, aluminum indium nitride, aluminum gallium arsenide, or any other kind of ternary alloy as per requirement of your own devices. So in today's video, the focus is not going to demonstrate the entire performance of the device, but my focus is going to be on these two layers. This layer over here, which is based on aluminum gallium nitride, and then this second layer. And I'm not going to talk about the context, like for example, in the actual structure I have a drain, source, and gate, but I'm not going to focus on the contacts as well. My focus is going to be on these two layers. Here we actually form a heterojunction between the aluminum gallium nitride and the gallium nitride layer, and the heterojunction is created by different bandgap materials forming a quantum well. We can see the quantum well using by going to tools, then cut line, then draw a cut line across this interface. Left click in this right pane, then right click, go to display, and here we want to see the energy band diagram of this structure. So click on EC of T, EV of T, electron QFL, and hole QFL, and you can see this quantum well over here at this interface between the aluminum gallium nitride film and the gallium nitride layer. So a two-dimensional electron gas occurs when electrons are confined to an interface between these two materials. these electrons can move quickly without colliding with any impurities and from which they cannot escape. The effect of this is the creation of a very thin layer of highly mobile conducting electrons with very high concentration, giving the channel very low resistivity, or to put it another way, high electron mobility. That's why we call it high electron mobility transistors. HEMTs make use of high mobility electrons generated using this heterojunction over here, or in the device structure it's over here. In HEMTs, the electric current flows between a drain and a source element via the two-dimensional electron gas, which is located at the interface between the two layers of different band gaps, and that's why we call it the heterojunction. So I'm going to close this figure, and here is the code part. So here is the DAC build environment for Silvaco TCAD, and here is the code part. So I start with Go Atlas, and then I introduce the meshing over here. My device runs from 0 to 10 micrometers along the X direction. You can see it over here as well. So 0 to 10 micrometers along the X direction, and 0 to 3 micrometers along the Y direction. In this part, I have introduced meshing, where I introduced denser meshing for the thinner layers. So I right click on the structure, go display, and click on the meshing, hit apply, OK. So you can see that I have introduced denser meshing for the thinner layers, and also along the regions where we have the interfaces. And since for this structure I'm mostly just interested in this region, so I basically introduced denser meshing over here. Now the next part is introduction of the regions. Region number 1 runs from 0 to 10 micrometers along the X direction, and from 0 to 0.2 micrometers, or in other words you can say 200 nanometers along the Y direction. The material is aluminum gallium nitride, and here as an example for the first run I have fixed the aluminum content. So the X composition over here represents, or you can say corresponds to the aluminum content. So I'm keeping a fixed aluminum content of 70% for the first run, and then later in the second run of the simulation I'm going to demonstrate how to perform the compositional grading. And so basically this is a 200 nanometers thickness aluminum gallium nitride layer, and if I draw a cut line across the interface, then go to display, and then here if I click on the band gap, hit apply, you can see that in the first one I have fixed the band gap at approximately 5.05 electron volts for the aluminum gallium nitride layer. And the band gap of gallium nitride is around 3.43-ish electron volts. Roughly you can say 3.4, approximately 3.4 electron volts. So in the first run I'm keeping the band gap fixed, and then later in the second run I'm going to introduce how to perform the compositional grading. And then region number 2 is gallium nitride running from 200 nanometers to 1.98 micrometers. As you can see in this structure, from 200 nanometers to 1.98 micrometers. Then region number 3 is aluminum nitride nucleation layer running from 1.98 micrometers to 2 micrometers. You can see it over here, really thin layer of aluminum nitride. We call it the nucleation layer, and the nucleation layer is actually crucial from growth point of view. And then region number 4 runs from 2 micrometers to 3 micrometers along the y direction, and it's actually sapphire substrate. So this blue region over here corresponds to sapphire, and it's running from 2 to 3 micrometers. And then here in this part, I have introduced different contacts, the source region, the drain region, the gate region, and the substrate region. If I right click on the structure, go to display, and then click on this icon, hit apply, and then click OK. You can see all the layers. You can see the drain, the gate, and the source, and the substrate. But for this video, I'm not going to focus on the IV characteristics of the device, so we are basically going to skip that part. So okay. Then I save this structure, then I run another module of Atlas, and then I import the structure that I saved in the previous block. And then here we have introduced the work functions for the different contacts, a work function of 5 for the gate contact, 3.93 for the source, and 3.93 for the drain as well. And then I have introduced different models. For example, the first model, in the first line here, I have introduced the models of print and SRH. Print model basically prints the status of all models, a variety of coefficients and constants in this runtime window. This model over here enables the low field mobility model. Then I've introduced polarization and the strain models over here as well. Polarization enables the automatic calculations of interface charges due to spontaneous and piezoelectric polarization. Spontaneous polarization occurs due to hexagonal structure and asymmetry in gallium nitride, aluminum nitride, indium nitride, and their ternary alloys. Similarly, piezoelectric polarization occurs due to the lattice mismatch in these materials. And then I have this command calc.strain, which specifies that the strain in the region is calculated from the lattice mismatch with adjacent region. This command over here specifies a constant scale factor multiplied by the calculated spontaneous and piezoelectric polarization charges. And it basically is related, or you can say it corresponds to polarization in word side materials. Here we output different parameters: conduction, valence, energy levels, polarization charges, electron and hole mobilities, different recombination phenomenon, and current flow lines as well. Several different methods can be used for the numerical calculations in order to find the solutions to semiconductor device problems. Basically, there are 3 kinds of solution techniques: Gummel, Newton, and Bloch. The Gummel method is useful when the system of equations has only linear convergence. The Newton method is useful when the system of equations has quadratic convergence. The Newton method may, however, spend extra time solving for quantities. Newton also requires a more accurate initial guess to the problem to obtain convergence. And here I'm actually using the Newton method in order to find the numerical solution of my code. Then we see maxtrap, and this basically means over here that this procedure is repeated up to a maximum number of 20 tries set by the method parameter, and once the convergence is obtained, the bias steps are then increased again. So if I run the simulation, and if the simulation is not able to perform convergence, then it's going to reduce the bias step by half, and it's going to continue doing it subsequently unless it finds a convergence to the problem. And if after 20 tries it's still not able to find convergence, then it's just going to abort the operation and it terminates the simulation. Then here we are this actually gives an initial guess of the structure, and here I'm saving the structure with this name, and then we use Tony plot command in order to plot the structure. So here is and then the query actually finally terminates running the program. And after that I have a long code, but this is not relevant to today's videos, so I'm going to skip that part. So basically our focus is going to be on region number 1 and region number 2 in today's video. And as I already mentioned that in the first run, I'm going to keep the aluminum gallium content, the aluminum content in the aluminum gallium nitride layer fixed at a composition of 70% aluminum content in the aluminum gallium nitride film. So let us run the simulation. Here is our simulated structure. Let us focus on this region over here. This is the aluminum gallium nitride layer, and this is the gallium nitride layer. In order to look at the energy band gaps, I go to Tools, Cut Lines, draw a cut line over here, and then right click on the right figure, go to Display, and I want to see the energy band gap, so then hit Apply. So as you can see that the energy band gap for this 200 nanometers aluminum gallium nitride film is fixed at approximately 5.05 electron volts. And then this is the gallium nitride layer, so it abruptly transitions to the gallium nitride layer, and its band gap is fixed at 3.4 electron volts. Similarly, we can also see the energy band diagram of this structure, or you can say energy band diagram of this heterojunction. Here is the energy band diagram of the heterojunction. Now what we want to do is we want to introduce compositional grading in the aluminum gallium nitride layer, and there could be two approaches. One approach is to have higher aluminum content at the bottom and then lower aluminum content at the top, and another approach would be lower aluminum content at the bottom and higher aluminum content at the top. So I'm gonna simulate both the scenarios for you, but before doing that, let me show you some references where different researchers have used compositional grading in aluminum gallium nitride for a variety of applications. For example, this first reference is about a graded aluminum gallium nitride composition super lattice. So for comparison, here are two energy band diagrams. Look at figure B and figure C, and they have used 6 pairs of this super lattice, in which they are actually varying the aluminum content of the middle layer. So as you can see over here for figure B, the band gap from one end to the other end, or you can say from the left end to the right end for these quantum wells, is actually the same. But if you focus on figure C, you can see that the band gap of this quantum well actually, so if you focus on this quantum well, you can see that the band gap of this quantum well gradually increases, moving from left to right. So this is one application where they have used it, where they have used compositional grading of aluminum gallium nitride films in super lattice. Then here is another reference corresponding to conduction mechanism in compositionally graded aluminum gallium nitride films. And here is the entire structure, where you can see compositional grading for the aluminum gallium nitride films, film from 40% aluminum to 10% aluminum along a thickness of 200 nanometers. Here is another paper related to making contacts to silicon doped aluminum nitride films using graded aluminum gallium nitride contact layer. And let me take you to the corresponding figure. So here they have grown a structure where the substrate is silicon carbide based, then an undoped aluminum nitride film 800 nanometer thickness, then a silicon doped aluminum nitride film. And it's not easy to make contact to aluminum nitride, whether it's p-type doped or n-type doped. Advanced Semiconductor Technology Facility, run by Professor Dr. William Allen Doolittle at Georgia Tech, is the best in terms of achieving both p-type and n-type aluminum nitride films. In fact, they are the pioneers in this field. But still, the next challenge is how to make good contacts to the undoped, p-type doped, and n-type doped aluminum nitride film. And it's challenging because of several reasons. First of all, the electron affinity of aluminum nitride is pretty low, ranging from 0.6 to 1.9 electron volts. Different sources mention different electron affinity. Personally, I've seen a lot of references mentioning 1.9 electron volts electron affinity for aluminum nitride film, but it's still pretty low. So it's not easy to make contacts to aluminum nitride film. So one approach to make good contacts would be to grow graded aluminum gallium nitride films and also doped at the same time, where they are actually grading it from 100% over here at this interface to 55% towards the top layer. And if you are familiar with the aluminum gallium nitride films, we know that we can achieve high carrier concentration for both electrons and holes for up to approximately 55%, or maybe at max up to 60% aluminum content in aluminum gallium nitride film. So we know for sure that this content of aluminum gallium nitride film definitely gives us good carrier concentration, and it's going to be, and then we etch down this structure to the n-type doped aluminum nitride films and deposit metal contacts on top of that, resulting eventually resulting in making good contacts to the silicon doped aluminum nitride films. So this is another crucial application of the video that involves compositional grading in ternary alloys. And then here is another reference in which they have used the application of compositional grading of aluminum gallium nitride film in a HEMT structure. So on the left side we have this aluminum gallium nitride layer, 11 nanometer thick without the compositional grading, and then on the right side we have the same layer with the compositional. It's actually this layer over here with the compositional grading from 0 to 10% for aluminum, having a thickness of 10 nanometers. So my point is, there are actually enormous applications of today's video, and you can actually optimize it for your kind of application. So I already showed you how to include the aluminum gallium nitride layer with a fixed aluminum content of 70%. Now I'm going to show you how to compositionally grade it from one interface to the other. Now, for example, first what we want to do is having a lower aluminum content at the top and higher aluminum content over here at the bottom of the aluminum gallium nitride layer. So the band gap is going to be smaller over here at the top and then higher over here at the heterojunction. So for doing that, it's really simple and straightforward. What we do is for example, we want a 10% aluminum content over here at the top and 70% aluminum content over here at the bottom of the aluminum gallium nitride layer. So for that, we introduce these commands: compx.top is equal to 0.1 and compx.bottom is equal to 0.7. Then we run the program. The structure is simulated. Let us focus on this region of interest. We go to Tools, Cut Line, draw a cut line over here at this interface. Then left click on the right figure, or right click, click on Display. You want to see the energy band diagram, the energy band gap values first, hit Apply. So as you can see that the band gap is smoothly increasing from here towards the bottom, or you can say in this figure from left towards the right, from approximately 3.6 electron volts for 10% aluminum in aluminum gallium nitride to approximately 5.05 electron volts for 70% aluminum in aluminum gallium nitride film. And then here at the heterojunction, we have the gallium nitride film below it. So as you can see towards the right in this figure, the band gap is fixed at approximately 3.4 electron volts. You can also see the energy band diagram. hit apply. So here is the energy band diagram. Here you can see that the band gap is narrow over here towards the top, and it's getting wider towards the heterojunction. Similarly, what we can do is we can reverse the order of the compositions. So this way we have 70% composition at the top and 10% composition at the bottom. And I have already simulated the structure. So as you can see, towards the, if we have 70% composition over here at the top, then we will have a wider band gap at the top and narrower band gap at the bottom. Similarly, we can replace region number 2 with aluminum nitride if we want to make a contact to it, and we can use some additional features to make good calculations for making contacts to aluminum nitride. So I have simulated this structure as well, but here I kept a lower content at the top and higher content at the bottom. This makes more sense. So now this is aluminum gallium nitride grown on top of aluminum nitride, where we have lower aluminum content at the top and higher content over here at the bottom. So this way we have a narrower band gap at the top and wider band gap at the bottom. And then if we do both the aluminum nitride film and the aluminum gallium nitride film, then we will have higher carrier concentration over here at the top, and then we can make really good contacts to the entire structure. And then if you reverse the order of these, then the band gap order of the heterojunction also reverses. So that is pretty much it for today's video. We covered compositional grading and ternary alloys. Now you can use these techniques to optimize your own designs, and you can also include other kind of materials as well in Silvaco TCAD. If you found this video helpful, make sure to give it a thumbs up and subscribe for more tutorials like this. Got any questions or suggestions for future videos? Drop them in the comments below. I would love to hear from you. Thanks for watching and see you in the next video. Happy simulating. Adios.